Okay, what if I told you that it's possible to hear a beam of light? I know it sounds like something straight out of science fiction, right? But it is a very real phenomenon, one that was discovered over 100 years ago. It's a story of how a forgotten scientific curiosity became a modern-day superpower. So, how did that happen? Let's dive in. So, let's head back to 1880. Alexander Graham Bell. Yep, the same guy who invented the telephone. He stumbled upon something, well, kind of bizarre. He was working on a really cool project to transmit sound on a beam of light. He called it the photophone, when he noticed this really strange side effect.
And this is the part that just blew everyone's minds. A solid object, this thin little disc, was making a sound you could actually hear, not because anything was hitting it or vibrating it, but simply because it was being hit with chopped up sunlight. Just think about that for a moment. No speakers, no electricity, just light, making a solid object sing.
Which brings us to the big, central mystery of it all. How in the world is it physically possible to hear light? What is the actual mechanism that turns silent particles of light into pressure waves our ears can detect?
Well, the answer isn't magic, even though it really sounds like it. It's a truly fascinating physical process. So let's break down exactly how light gets transformed into sound.
This whole phenomenon has a name, the photoacoustic effect. And the name really says it all, right? Photo, from the Greek word for light, and acoustic, for sound. At its heart, it's a direct conversion of light energy into sound energy, happening right there inside the material.
So here's how that transformation works step by step. First, you take a sample and you hit it with light that's blinking on and off really fast. We call that modulated. The sample absorbs that light energy, and just like a dark shirt on a sunny day, it heats up. As it heats, it expands a tiny bit. Now, because the light is blinking, the sample is heating and cooling, expanding and contracting over and over and over. This rapid pulsing creates a pressure wave. And what is a pressure wave? It's a sound wave, one that a super sensitive microphone can then pick up.
Now, what's really interesting is how this plays out with different types of materials. For gas, the whole process is very direct. You got a sealed chamber full of gas, and you shine that chopped laser beam through it. The gas molecules absorb the light, they heat up, and they create these little pressure pulses right there in the chamber. A microphone inside just listens to that sound.
But for solids, it's a bit more indirect, and honestly even cleverer. The solid absorbs the blinking light, and it heats up and cools down just the same. But here's the twist. The sound isn't coming from the solid itself vibrating, no. Instead, the solid transfers its heat to the super thin layer of gas that's touching its surface. It's that tiny layer of gas that expands and contracts, acting like a little invisible piston, creating the sound the microphone picks up. Bell's discovery was absolutely amazing, but for almost 100 years, it was little more than a scientific party trick. So how did this strange observation go from being a fun curiosity to an indispensable tool for modern science? Well, that's the next part of our story.
It's kind of hard to believe, but there was this massive, nearly 90-year gap where the effect was pretty much forgotten. Then, fast forward to the 1970s, a physicist named Alan Rosenzweig, and get this, he was working at Bell Labs of all places, he revisited the phenomenon. He's the one who developed a deep theoretical understanding that finally explained everything that was going on. And this is such a perfect example of the power of theory in science. Rosenzweig's work is what turned the photoacoustic effect from just a cool thing you could observe into a predictable, measurable, and incredibly powerful scientific technique. We call it Photoacoustic Spectroscopy, or PAS for short. All of a sudden, you could not only hear the light, you could understand exactly what that sound was telling you about the material.
So, what's the big deal? What problem did this brand new technique solve? Well, it tackled one of the single biggest headaches in science, trying to analyze things you literally can't see through.
I mean, just think about the limitations. For decades, if you wanted to analyze something using light, that light had to pass cleanly through it or reflect perfectly off it. That meant countless materials, powders, thick gels, biological tissues, soil, were basically total black boxes. They were too opaque or they scattered light in every direction. But photoacoustic spectroscopy, it just completely sidesteps that whole problem. It doesn't care if light scatters or reflects. It only listens for the sound that's produced by the light that gets absorbed. And that right there is its revolutionary advantage.
Oh, but it gets even better. PAS has a true superpower. It's called depth profiling. By changing how fast you chop that light beam, you can actually control how deep the heat wave goes into the sample. If you chop the light really fast, you only hear the sound from the very surface. But if you slow the chopping down, you start to listen to signals coming from deeper inside the material.
It's almost like having acoustic X-ray vision for opaque objects.
This ability to analyze opaque materials and, peek beneath the surface is what has turned this once-forgotten effect into a genuine scientific superpower with an absolutely incredible range of applications.
The applications today are just staggering. I mean, check this out. Scientists use it to analyze things like blood and skin without any complicated prep. Environmental agencies use it to monitor tiny trace amounts of pollutants in the air. You can use it to measure the precise amount of medicine in a thick ointment, detect malaria parasites in a blood sample, and analyze super-concentrated dyes that are impossible for other methods to handle. It's even used to study the aging process in human eye lenses.
So, the journey is complete. We've gone all the way from Alexander Graham Bell being mystified by a disk humming in the sun to a sophisticated modern technology that lets us analyze the chemical makeup of pretty much anything, no matter how opaque or messy it is. We literally learned to hear light.
It really makes you wonder, doesn't it? Bell's discovery waited for almost a century for the right theory and the right technology to come along and unlock its potential. And that leaves us with a final thought. What other seemingly impossible phenomena are out there all around us, just waiting for us to figure out how to listen?